All right, last week we looked at some addition rules, and the addition rule that we were to use depended upon whether or not our events were mutually exclusive or not. Well, there's two multiplication rules, and which one we are to use depends upon whether or not our events are independent events or not. So the place to open up this section is to define what it means for two or more events to be independent. We say that two or more events are independent if the occurrence of one of the event in no way, shape, or form affects the probability of the occurrence of any other event. If that's the case, then we say the events are independent. Here's some examples of some independent events. Suppose that event A is that I roll a 4 on a die, and event B is that you flip a head on your coin. Those events, ladies and gentlemen, are independent events because they do not affect each other's probability of occurrence. Another example of independent events. Suppose I define event A to be that it rains somewhere on planet Earth, and event B to be that it rains somewhere on planet Venus. For all practical purposes, those events, A and B, are independent events. What happens on Earth pretty much stays on Earth and vice versa. When you flip a coin 3 times, those 3 flips of the coin are independent events. The second flip of a coin in no way, shape, or form remembers what happened on the first flip. So coin flips and when rolling a die, those are called memoryless trials in the sense that any trial does not remember what happened on any previous trials. Those are always independent events. Any experiment with replacement is defined to be independent events. So hopefully with those examples, we have a better idea as to what it means for events to be independent. Now, if events are not independent, then they are dependent. Examples of dependent events would be if I draw 2 cards from a deck, and the first card I draw from the deck, I leave it out of the deck, that is an experiment without replacement, that will affect the probability of what occurs on the second draw. So any experiment that is conducted without replacement involves events that are dependent, not independent. All right. Another example of dependent events would be parking in a no parking zone and getting a parking ticket. I think it's safe to say that if you do that, you run the risk of getting a parking ticket. So those are dependent events. Those are not independent events. Here's another example. Suppose I define event A to be that I choose a 6 from a deck of cards, and I define event B to be that I choose a diamond from a deck of cards. Well, those are not independent events, especially if I do the experiment without replacement. Now, I have a question for you. If two or more events are mutually exclusive, does that also imply that they are necessarily independent events? The answer is no. For instance, if I define event A to be, again, that it rains on planet Earth somewhere, and event B to be that it rains on planet Venus, okay, those events are not mutually exclusive because those events could occur simultaneously. However, those events are independent events. All right. So don't think for a moment, ladies and gentlemen, that independent events are and have to be necessarily mutually exclusive. They may be, but they do not necessarily have to be. So independence does not imply mutually exclusiveness and vice versa. All right, here's the first multiplication rule. Suppose we have 2 independent events, A and B, and I want to compute this and probability, the probability of A and B occurring at the same time. Well, because these are independent events, we would literally multiply the individual probabilities together to compute this and probability. Or probabilities suggest an addition rule, and probabilities are going to suggest a multiplication rule. So or means addition, and means multiplication. This is your first multiplication rule right here. All right. As part of a psychology experiment on perception and memory, colored balls are picked from an urn. The urn contains 3 red balls and 2 green balls and 5 white balls. A ball is picked and its color is noted. Then it is replaced. A second ball is then picked and its color is noted. Find the probability of each of these. Find the probability of picking 2 green balls, and find the probability of getting a green ball and then a white ball. Since this is an experiment with replacement, okay, these events, these trials of choosing 2 balls are independent of each other. All right, so let's see if we can negotiate this. The first question there in A is the probability of selecting 2 green balls. So they want us to compute the probability that the first selection is a green ball and the second selection yields a green ball. And means a multiplication rule. Since these events are independent of each other, because this is an experiment with replacement, in other words, what you select on the first trial does not affect what happens on the second selection because you're replacing the first trial back into the lot. So this is going to be equal to the product that the first ball selected is green times the product the second ball selected is green. It's as simple as that. So what is the probability that the first ball selected is green? Well, it says there's 3 red balls in this urn. There's 2 green balls and 5 white balls. So the probability of selecting 2 green balls in succession with replacement, the probability of selecting the first ball and it being green would be 2 over 10 times the probability. So if we select a green ball in the first selection, we replace it back into the urn, and then we reach in again and pull out a second ball. Probability of second ball is green will also be 2 over 10. So the probability of getting a green ball, replacing it, and then selecting the green ball again would be 4/100ths, or 0.04 or a 4% chance. Any questions how we computed that probability there? All right, that's part A. For part B, what is the probability of picking a green ball and then replacing it and then picking a white ball? So the probability that the first selection yields a green ball and the second selection yields a white ball. Well, that's going to be equal to, since these are independent events, the probability of the first selection is green, and then we're going to multiply that by the probability that the second selection is white. So the probability we select a green ball in the first selection would be 2/10 times the probability of selecting a white ball on the second selection would be 5/10. So 10/100ths, or 0.1 or 10% chance that I will select a green ball and then a white ball in succession, assuming this is an experiment with replacement. Any questions how I computed that and probability there? All right, here's another example. 3 cards are drawn from a deck. After each card is drawn, its denomination and suit are noted, and it's mixed back into the deck. In other words, replaced back into the deck before the next card is drawn. So this, again, is an experiment with replacement. Because of that, trials or draws from this deck are deemed as being independent trials because it's an experiment with replacement. Okay. So for classwork number 1, I want you to compute the probability that all 3 draws from the deck yield kings. And then for C, compute the probability of getting 3 clubs in a row. This is assuming, again, that when we select a card from the deck, We note its denomination and its color, and we replace it back into the deck, shuffle the deck, and then reach in and pull out a second card. Note its denomination and color, put it back into the deck, shuffle the deck, reach back in and pull out a third card, and note its denomination and color. Classwork number 1, do B and C. B and C for classwork 1. All right. So Assuming we randomize the deck, reach in and pull out 3 cards in succession, each time with replacement, what's the probability that we pull out 3 kings? A king on the first, and a king on the second, and a king on the third. This is going to be equal to the product of pulling out a king on the first, and the product of pulling out a king on the second, and pulling out a king on the third. That's going to be 4/52 times 4/52 times 4/52, which is 1/13 times itself 3 times, which is 1/2197. Anybody get this correct here? This probability. Again, this is an experiment with replacement. In a similar fashion, what's the probability that we reach in 3 times into a deck and pull out 3 clubs, each time with replacement? It's going to be 13/52 times 13/52 times 13/52, which is 1/4 times 1/4 times 1/4, which is 1/64. All right. Anybody get these correct? Are we understanding what's going on with the first multiplication? The first multiplication rule.
I get it.
What's that? You got it?
Yep.
The key assumption is that the trials of the experiment are independent of each other. That's how we can use this rule. If they're not independent, we cannot be using this multiplication rule.
What it is I did the second question as the first question. I mistakenly mixed up the questions.
I see. But you got them correct, right?
Yes.
Wow. That's the important thing. This is just saying that if you pull a sample from a very large population, then your sample is considered to be independent, an independent sample. All right. So according to this report by Market Watch, 70% of college grads will leave college with some student debt. If 4 graduating seniors are chosen randomly and asked if they have student debt, are these student responses independent? For all practical purposes, we would say they are, because the sample is so much smaller than the overall population size. Usually the rule of thumb is as long as the sample is no more than 5% of the population, then your chosen sample subjects are independently chosen. Understood. All right, so what would be the probability that all 4 will graduate with some student debt? Well, that's going to be 0.70 times itself 4 times. So the probability that you randomly choose 4 graduates and all of them indicate that they will graduate with some sort of debt would be 0.7 raised to the 4th power, or 0.2401, about 24% chance. All right, multiplication rule number 2. Let me explain what's going on with this rule here. Suppose I have a container and I have 4 red balls in the container, let's say 3 green and maybe 10 white balls. Suppose I conduct an experiment with replacement. What would be the probability that I reach in for the first time and pull out a green ball, and then the second selection is a red ball, And the third selection is a white ball. Well, since this experiment is conducted with replacement, if I reach in and pull out a green ball, I replace it right back into the container. So therefore, these events or trials are independent of one another. Being the case, this probability is going to be computed by multiplying these individual probabilities together. The probability that the first selection is green, second selection is red, third selection is white. Probability of reaching and pulling out a green ball on the first selection is going to be 3/17 times the probability the second selection yields a red ball is going to be 4/17 times the third selection being white would be 10/17. 3 times 4 is 12 times 10 is 120. 120/17 times itself 3 times, and let's see, what's that going to give us here? 17 times 17 times 17. 4,913. So that's the probability of pulling out a green ball on the first selection, a red ball on the second selection, and a white ball on the third selection with replacement. Okay, you can see that that's a small probability. All right, suppose we conduct an experiment now, a second experiment without replacement. What would be the probability that the first selection is green and the second selection is red and the third selection is white? Well, these events are no longer independent. These are called dependent events because this experiment is going to be without replacement. So if on the first selection, I select a green ball, okay, and I keep the green ball out of the container, that reduces the number of green balls down to 2, and that's going to affect subsequent probabilities of other selections. So to compute this probability where these events are no longer independent, they are dependent, would be to, first of all, compute the probability that the first selection is green times this conditional probability. Given that the first ball selected is green, what is the probability then that the second ball selected is red? Times, given that the first ball is green and the second ball selected is red, what then would be the probability that the third ball is white? These are called conditional probabilities because they are conditional upon what has happened on previous selections. So the probability that the first ball selected is green is going to be 3/17 times, but we keep the green ball out. And then we reach in a second time, then given that the first ball selected is green and we keep it out of the container, we do not replace it. What is the probability the second ball selected is going to be red? That's going to be 4/16 times, and then we keep the red ball out of the container. Don't replace it. That reduces the number of red balls down to 3 remaining. Then we reach in a third time, given that the first selection is green and the second selection is red, and we keep those out of the container, we do not replace them back in. What then would be the probability that the third selection would be white? That would be 10/15. And this is your probability of selecting a green ball and a red ball and a white ball if we conduct the experiment without replacement. Notice It's a lot different than the probability that we got when we replaced the balls. Okay, totally different probability. This is going to be 120 over 4,080.
Which that lowers down to 1/34.
All right. So the bottom line is, ladies and gentlemen, is if you conduct an experiment with replacement, your events are independent, your trials. The probability is totally different as if you conduct the experiment without replacement. Then your trials are no longer independent. They are dependent, and you have to speak in terms of what is called a conditional probability. Okay? All right. So that makes sense. They're this example, these two examples and how they differ. So these events are independent events here. And these events are dependent. All right. So in general, this is the second multiplication rule. If events A and B are dependent events, not independent, then the probability of A and B occurring at the same time or in succession is going to be equal to the probability event A has occurred times this conditional probability. Given that event A has occurred, the probability then that event B will occur. This is the second multiplication rule. You have to use this rule if your events are not independent. This is called a conditional probability. And again, the way you read it is, given that, this vertical bar means the phrase given that event A has occurred, what is the probability event B will occur? Given that event A has occurred, what is the probability event B will occur? Conditional probability rule. That's the second multiplication rule. All right. 3 cards are drawn from an ordinary deck and not replaced. This is an experiment without replacement. Because it is, ladies and gentlemen, I want you to do this for classwork number 2, A, B, C, and D. I want you to compute all of these probabilities, assuming that the choice selections from the deck are done without replacement. See if you can go ahead and crank out these probabilities. Call this classwork number 2, A through D. Without replacement now, not with replacement. So these are dependent selections now, dependent events.
So for B, are we taking out the 3 jacks out of the 52 cards?
For which one now?
Like to do B, would we take out the 3 jacks that we did in A? You know what I mean?
No. These are separate problems.
Okay.
Separate problems with 3 selections each. Okay. All right. Try to compute these problems.
I have a advising appointment. I have to go. I'll read over the lecture later and do the classwork. I gotta go. I don't get it. I'm not understanding any of it. But I think I got A.
All right, let's take a look at these then. So what's the probability that we reach into a deck and pull out 3 cards in succession without replacement? All these events therefore are dependent. So what's the probability that we pull out the first selection is a jack, and the second selection is a jack, and the third selection is a jack? Well, that's going to be equal to the probability the first selection is a jack, which is 4/52, times, given the first selection is a jack and we keep it out of the deck, we do not replace it back into the deck. How many jacks remain? 3/51 cards left. That's the probability of selecting a jack on the second draw. Times, given that the first card is selected as a jack and the second card selected as a jack, and we keep them out of the deck, now our deck's been reduced down to 50 cards. So what's the probability that the third card chosen is a jack? Well, there's only 2 jacks left because 2 of the jacks are kept out on the first and second selection. 2/50. This is the probability of selecting 3 jacks in succession from a deck of cards without replacement. That's what the probability reduces down to. Did anybody get that? Anybody?
I did.
Yes.
Next problem. What's the probability of pulling out an ace, a king, and a queen in succession in that order without replacement? That's going to be equal to the probability, first of all, we pull out an ace. And that is going to be what? 4/52. Times, given the first selection extracted from the deck is an ace and we keep it out of the deck, what then would be the probability that the second selection will be a king? Well, there's 4 kings, but only 51 cards left. Because we kept the first selection, the ace, out of the deck, we did not replace it. Times, given the first selection is an ace and the second selection is a king, and we keep both those cards out of the deck, we do not replace them. What then would be the probability that the third selection will be a queen? Well, there's 4 queens, but there's only 50 cards left now. 4/50. Multiply all these together, you get your probability. Anybody get this?
Yes.
C. What's the probability of selecting a club and a spade and a heart in succession in this order without replacement? These events are dependent events because this experiment is without replacement. Hence, that's going to be equal to the probability the first selection is a club, which is 13/52, times, given the first selection is a club and we keep it out of the deck, what's the probability the second selection will be a spade? That'll be 13/51, times, given the first selection is a club and the second selection is a spade, those cards are kept out of the deck. What then is the probability that the third selection will yield a heart? That would be 13 over only 50 cards left. Multiply these together, you get that probability. All right. Did anybody get this here? So,
Yeah.
Alicia, is this making any more sense now that I've gone over it or not?
And yes,
You see, it's without replacement. And because of that, the subsequent probabilities keep changing. okay, for subsequent selections. That's why these are dependent events, because the probability of a subsequent event occurring depends upon and is conditional upon what has happened on previous events. All right, last problem here. D, what's the probability I reach into this deck and pull out a club, and a club in succession without replacement? Well, that's going to be equal to the probability that the first selection is a club, which is going to be 13 over 52, times, given the first selection is a club and I keep that club out of the deck, what then is the probability I reach in a second time and pull out a club? That'll be only 12 over 51. Times, given that the first selection is a club and the second selection is a club, and we keep these two cards out of the deck, what then would be the probability I reach in and the third card selected would be a club? Now we're down to 11 clubs left over 50 cards left. Multiply these together, you have your probability of this occurring. So you can see that there is a huge difference in computing and probabilities depending upon whether the events are or are not independent events. If they're independent events, the probabilities remain the same. If they're not independent events, they're dependent events, we can see that probabilities change, okay? And you have to use what's called a conditional probability. All right, so that is illustrating the use of the second multiplication rule. Now, I didn't reduce some of my fractions all the way down. I could have reduced them a little bit more. All right. So, ladies and gentlemen, we speak in terms of conditional probability. And this is another way to write the second multiplication rule, is to write it as P, the probability of events A and B occurring, divided by the probability of event A occurring, is equal to this conditional probability given event A has occurred that B will occur. This is the same rule that I wrote down on my on the lecture notes. Nothing changes there. Okay, hold on. I don't want to get into that problem there. Let's get into this problem. Let's look at this data table here. Hate crimes are defined to be crimes in which the victim is targeted because of one or more personal characteristics, such as race, religion, and sexual orientation. The table below lists the motivation for certain hate crimes as reported by the FBI for the year 2020. So we got different motivations for crimes, and we got crimes against people versus crimes against property versus crimes against society. We have our column totals at the bottom and our row totals off to the right. Question, how many, ladies and gentlemen, crimes were surveyed for this investigation? How many total crimes?
7,829.
That's correct. 7,829 crimes were investigated, and this is how they basically find their location in this contingency or frequency table here, okay? All right. Wait a minute here. Does this look like one for sexual orientation for crimes against person? Does that look like 1.061?
Yes,
That should be a comma, shouldn't it? That's a typo.
yes.
Everybody see that there? Okay. Just noting that there. That should be a comma. That's 1,061. All right. Okay, ladies and gentlemen, knowing this table, let's see if we can answer some questions maybe. And let's see if I can snip this table so we can carry it over to other pages of this investigation instead of having to flip back. All right, let's go onward now. See if I can bring this table up, but the problem now is it's hiding everything, which is stupid. I can maybe shrink it down, still be able to see
You
it.
can move it by grabbing that bar right there. Just click on that, yeah.
Yeah, move it, and I shrunk it down, but a little bit too much here. Hold on a second. Let's see if I can bring it down. Okay, but let's see if I can bring the top down though. Oh, darn, that does that. Okay. Well, golly, where to put this? Come on, you silly thing. Well, ladies and gentlemen, I'll tell you what. You do part A, all right? Everybody do A for a classwork number 3 here. Find the probability that a hate crime was racially motivated, given that, I'm going to give you a hint on this problem. Given that it was a crime against a person. I'll tell you what, I'll do this one and I'll have you do B for classwork. So look at, ladies and gentlemen, when you see the phrase given that in a probability question, it's understood this is a conditional probability that is needed here, because given that suggests the conditional probability. That means the events in question are not independent, they are dependent events. Now, this is how it works. Given that it was a crime against persons, you know what that does? Given that it was a crime committed against persons, that locks us into the first column. We're locked in to the first column, because that's what given that does. It locks you into a column or a table of a column or a row of a table. So given that it was a crime committed against a person, find the probability then that a hate crime was racially motivated. Well, ladies and gentlemen, of the 5,045 crimes against persons that were locked into, how many were racially motivated? Racially motivated. Right here, 3,000.
3,392 over.
Right. So
54.
therefore, you know what? The probability that a hate crime was racially motivated. I'm just going to say race for short, because I don't like writing with the mouse. It drives me nuts. Given that the crime was against a what? Against a person. So given that the crime committed was against a person, locks us again into this first column here. Okay, locked in the first column, therefore, what is the probability that it was racially motivated? Well, that would be 3,392. Divided by not the grand total, not divided by 7829, no, divided by 5,045, because we're locked into the first column. That's your probability. That's your answer to part A. So be careful when it says given that when they give you a table, a frequency table, given that means you're going to be locked into a column or a row. And so you do not divide by the grand total. You divide only by the row or only by the total of the row or column you're locked into. Okay. All right. Let me give you this question here. Now listen very carefully. What's the probability I randomly select one of these 7,829 crimes, and the crime was motivated by religion? What's the probability if I randomly select one of these crimes that it was religiously motivated? What would be the answer to that question?
1,650 over 7,829.
That's correct. In that question, did you hear the phrase given that anywhere? Did you ever hear given that?
Yes.
Wait, in the question, here was my question again. If I randomly select one of these crimes, what is the probability that it was religiously motivated? Did you hear the phrase given that anywhere in there?
No.
No. And because you never heard the phrase given that in there, we are not locked into a row or a column. Does that make sense? And that's why we're dividing by the grand total. Now listen to this question. Given that a crime was motivated by sexual orientation, what is the probability that the crime was against property? Let me say it again. Given that a crime was motivated by sexual orientation, what is the probability that it was against property?
329 over 2,570.
It'd be 324 over 2,500.
Oh, yeah.
Okay, you're close, but it's still not correct. Listen one more time. Given that a crime was motivated by sexual orientation, What is the probability that the crime committed was against property? Given that the motivation of the crime was sexual orientation, what is the probability that it was against property?
Is it 324 over 1,395?
That's it. Ladies and gentlemen, because I'm saying, given that the crime was sexually oriented in motivation, that locks us into the what? Third row. Do you agree? We're locked into the third row. Okay, then what is the probability that it was committed against property? That's going to be 324 divided by 1,395. All right, here's another question.
Wait, why didn't you do that on the first one then? Because
that?
the other one was race against person, but you used the total on the crimes against persons and not.
Because against persons comes after the vertical line, the vertical bar here in my conditional probability. That means we are to read this as, given that the crime was against a person, given that the crime was against a person, that locks us into the first column then. You see that? Then what is the probability that it was racially motivated? That's 3392 over what? 5,045. Okay. Now, what if I said this? Given that the crime was against society, given that the crime was against society, where am I locked into this table? Given that the crime was against society,
The fourth row,
I would be row?
fourth column,
What column?
4.
Yeah, given that the crime committed was against society locks me into this column. Do you agree? Then what is the
Yes.
probability that it was religiously motivated? You would say the probability would be?
34 over 214.
That's exactly right. Okay. Now listen to this question now. What is the probability that what is the probability that a crime was racially motivated and against society? Listen to that again now. What is the probability that a crime was racially motivated and against the society?
170 over 4,784.
All right, let me say that question one more time here. Okay. What's the probability that a crime was racially motivated and against society? Question. Did you ever hear the phrase given that in that question?
No,
No, meaning we're not locked into any row or column. So let me say it again. What's the probability that a crime was racially motivated and against society? What is the probability that a crime was racially motivated and against society?
170 over 4,784.
No, we're not locked into the first row. You never heard the phrase
Oh.
given that. You agree? You never heard given that. No. I just want you to compute the probability that a crime was racially motivated and was against society. That would just be 170 divided by what?
7,829.
Grand total, yeah, 7,829. All right, now listen to this. Given that a crime was racially motivated, what's the probability that it was against society?
34 over.
No, listen. Given that a crime was racially motivated, what is the probability it was against society?
170 over 214.
No. Given that a crime was racially motivated, locks us into what row or column?
Oh, the first row.
It
First
locks us
row.
into the first row. Given that a crime was racially motivated, what then would be the probability it was against society?
170 over 4,784.
That's right, 170 over 4,784. So you really got to kind of be careful and attentive as to, the words that are in your question or your probability question. If you ever see the phrase given that, then whatever comes after given that will lock you into a respective row or column of the table. Okay, and then you do not divide by the grand total in that case. If you don't see the phrase given that, then you're always going to divide by the grand total. All right. So just be careful on those type of probabilities. Okay. All right, so, let me get rid of all this garbage on here. So yeah, be careful. If you see the phrase given that, you need to understand that it locks you into a certain condition, okay? All right, let's see here. All right, let me see if I can move this table up here and. All right, ladies and gentlemen, now you do you do part B there. Classwork number whatever. I forgot to count. It's just a classwork. Number B, part B. Go ahead. Find the probability that a hate crime was against property given that it was motivated by the victim's sexual orientation. Okay, compute that probability.
That's not right.
Okay, based on how this probability reads here, am I locked into any row or column?
You're locked into the the fourth column.
All right, 'cause
No.
it says, given that the crime was motivated by the victim's sexual orientation, what row or column am I locked into?
The fourth row.
That's right. I'm locked into the sexual orientation row right here. This is where I'm locked in. Okay, I'm locked into this row. Now, locked into that row, then what is the probability that the crime was a hate crime, was against property?
324 over.
1,395.
That's right, 3,324 over 1,395. Is this making any more sense, ladies and gentlemen? If we
Okay,
want to
so
go,
you read what's after the given
that's
that
right.
first.
That's right. It's what comes after the phrase given that locks you in a row or column, okay? So what comes after the phrase given that is the column or row that you are locked into. Does that make sense? So yeah, that's how you read it. Okay, and then once you're locked into a row or column, then you go backwards into the word problem and compute the probability that they're asking. Okay. All right. Great. Let's see if we can go to our book and have some fun now in section let's see if we can go to our textbook and maybe have some fun. Did anybody go to the path of totality yesterday for that eclipse? I didn't. I was on campus, the main campus. It got pretty dark at around 3:11. Okay, hold on.
So I go there and I get in the line and the lady's like, what are we doing today? I said, I have my paper, but I was like, I don't have no debit card to that account. Never have. They've given me two that never work, and I just said, forget it because I never had one in the first place. Been there since I was 16. Can I just cash a check? She's like, okay. She was like, did you want to deposit it or something like that? And I was like,
All
yeah.
right.
I said, yeah. Then I was like, no, I don't want to deposit it because I don't have a debit card. So I got to go to the ATM every time I want money. I can't just swipe. So no, just cash it. She was like, well, why you don't have a debit?
All right, so let's see if we can go have some fun, ladies and gentlemen. Okay. All right, these problems are going to be coming out of section 10.8. This is the last section in chapter 10. This has been a long chapter. It'll be nice to wrap this chapter up. I don't know about you, but I think it's time. Wait a minute. Wrong. Oh, come on. Don't do this. All right, 10.8. Here we go. All right, so 10.8. And as always, take some time out to maybe look down through some examples in 10.8, some of which were not discussed during the PowerPoint, and it's only going to add to your understanding. All right, problem number 16 here. It says a national study of patients who were at an unhealthy weight found that 56% also have elevated blood pressure. If two such patients are selected, find the probability that both have elevated blood pressure. Now, so the probability they want us to compute is the probability that the first selected has what? High blood pressure. And the second patient selected has what? High blood pressure. I got a question for you, ladies and gentlemen. Are these independent or dependent events, these two selections? What do you think?
I think they're independent.
Yeah, for the most part, different people, that don't have any, family ties or biological ties are essentially independent. So being independent, what multiplication rule would I use? The first or the second one? First one. So this is going to be nothing more than the probability that the first has high blood pressure times the probability the second patient randomly selected has high blood pressure. Well, they told us in general that any patient selected would have the probability of them having high blood pressure would be 56%. So this is going to be 0.56 times 0.56. Get on your calculator, dial it up, and you have this and the probability computed. 0.56 times 0.56. 0.3136. Okay. Everybody see that thing? All right. Okay, I'm going to make up a problem, ladies and gentlemen. Suppose that I tell you the probability that a clock fails is like 10% chance. Suppose we have a very important interview tomorrow and we got to make sure we wake up. So what we do is we buy 5 of these clocks, 5 of these identical clocks. We wind them all up and we set the alarm to wake us up at a certain time tomorrow morning. I have a question for you then. What is the probability that the first fails and the second clock fails and the third clock fails and the fourth clock fails and the fifth clock fails? Got a question for you. Are these independent events? Are these independent clocks?
Yes.
For all practical purposes, yes, they are. What happens on clock number 2 could care less and does not have any idea as to what happens on any of the other clocks. And that goes for any other clock for that matter. These are all independent clocks, ladies and gentlemen. And so what you're about to witness is something very important used in critical systems in the real world. It's called the concept of redundancy. So do you agree this would be equal to the probability using the first multiplication rule that the first what fails times the probability the second clock fails times the probability the third clock fails times the probability the fourth clock fails times the probability the fifth clock fails. Well, they're all independent. And so therefore, this is going to be nothing more than what? 0.10 times itself 5 times, or 0.10 to the fifth power. Get on your calculator and dial it up now. So, ladies and gentlemen, what is the probability that I'm not going to wake up tomorrow morning for this important interview? The probability that none of these clocks go off and wake me up, thankfully, is very, very small. Do you agree? Very, very small. This illustrates the concept of redundancy. On critical systems, maybe an example would be like on an aircraft. If you have one system that goes down, and if that's the only critical system on board, then that means, you know, you're going to crash and lose your life. It might be wise to have a backup system. What do you think? Or maybe have a backup to a backup to a backup system in that case. Because what you're going to do is you're going to take what is a relatively high probability of failure, and by having backups of backups of backups, you're going to reduce the
Is that
probability.
part of classwork?
Well, this is not classwork.
Okay.
I'm just going over this one. So if you have a relatively high probability of failure of one system, and it's a critical system whereby its failure means your death, then, ladies and gentlemen, you might want to have a backup of a backup of a backup of a backup to drive that probability down to a very, very low value, so that the probability of total failure of all systems simultaneously is almost non-existent. That's what we want. That's what they use in the aviation industry, is they use redundant backup systems. And that would go for like any space missions too. They have backup systems. Got to have backup systems. I have a question. Has anybody ever gone sky jumping? Anybody ever jump out of a perfectly good airplane with a parachute on board, on a parachute? Anybody? Alicia, did you?
No.
I didn't either. Okay. And I don't think I ever would. But anybody go skydiving? Anybody? I'm just wondering, because I just want to know, do they have backup parachutes? You know, you'd really think they probably would, don't you? You would really
I've
think
seen
so.
movies where they do skydiving, and they usually do.
Huh, I know I would have one. In fact, this boy would have so many backup parachutes that I would look like the Stay Puft Marshmallow man. That's how big I'd look, with backups of backups of backups of backups. I could not imagine jumping out of a perfectly good airplane, ladies and gentlemen, with only one parachute, and risking and putting your life on that one parachute to open and function properly. Wow. That is risky. Okay. So this is the concept of redundancy, right? We're seeing how it works with the multiplication rule here with independent systems or independent events. All right, that's a good problem there. Okay, number 20. Let's see if you guys can figure this one out. If two people are chosen at random, what is the probability that they were both born in the month of December? Think about that, ladies and gentlemen. How would you do it? I'll give you a hint. We're trying to compute the probability that the first person chosen was born in December, and the second person randomly chosen, was born in December. Go ahead, see if you can figure that probability out. Number 20. This is classwork.
Would the person be replaced after they were picked?
Well, it's not really so much as whether we're replacing or not replacing them back into a container, because these people are not in a container. But the bottom line is we randomly select 2 people from the population. So what do you think, Liz? Do you think these people are independent of one another in general? In general, what would be your thinking? Would you lean more towards saying they're independent or dependent? What would be your thinking?
They're independent.
Generally, when you randomly select 2 people from a large population, they're deemed as being independent, okay, in general. All right. So that being the case, how would we compute the probability that we randomly select 2 people and their birthdays both falling in the month of December? Well, what is the probability that anybody's birthday will fall in December? How many Decembers are there out of 12 months?
1.
1/12 is the probability their birthday will occur in December, times the probability the second person's birthday will also occur in December, 1/12. Therefore, 1/144 would be the probability that if you randomly select 2 people, that both their birthdays will occur in the month of December. Make sense? That was the first multiplication rule that was used there. Did that problem make any sense now? Okay, armed with that problem, ladies and gentlemen, I want you now to do number 24. Just keep throwing it into the classwork. We got an open tab on our classwork here. What is the probability that a husband, wife, and daughter have the same birthday? I'm not going to say any more about this problem. I'm not going to give you any hints or anything. I want you to think about it, ladies and gentlemen, and see if you can compute this probability. Number 24. Call it a classwork. 24.
Hmm.
Well, so what do you think, ladies and gentlemen? Are these independent, these people? I know they're biologically related. Well, wait a minute. The daughter is related to the mom and dad. But the mom and dad are not biologically related. All right, whatever. Now, so we'll assume they're independent. Okay. So what's the probability that their birthdays all fall on the same day? Well, how many days are there out of the year? There's how many days in a year?
365.
So the probability the husband's birthday falls on a particular day is 1/365. Times the probability the wife's birthday falls on that same day would be 1/365. Times the probability the daughter's birthday falls on that same day would be 1/365. And there you go. That's the probability that all birthdays fall on the same day. So it's going to be 1/365 to the third power, which is going to be very, very small probability. Do you agree? To say the least, that all their birthdays fall on the same day. Very, very small chance. Hey, did anybody play that $1.3 billion Powerball where the drawing was Saturday night? Actually, Sunday morning. Anybody play that? Well, yours truly broke down and bought one ticket for $2. I did not match one number. Not even one number was matched of the five and the Powerball number. Anyways, ladies and gentlemen, I found out the odds of winning the Powerball. These are the odds. The odds are 1 to 292 million. That's your odds of winning with one ticket. One with one, well, the probability of winning with one ticket would be 1/200 and what? 92 million and one, correct? As you got to add these together. That'd be the probability of winning with one ticket. So, needless to say, it's pretty difficult to win the Powerball, right? That's why I very rarely play it. That's the first time I played that Powerball in, gosh, 20 some years. Okay. No luck. I'm still here teaching. Do you agree? All right. Let's go on, Lindon. Yeah, let's see. Let's see if we can get into another problem here. Let's see, we already did one like that. All right, let's get down into problems like 51. And here's a table here that's to be used for problems 51 through 54. Do we all see that table there? This is a survey of 200 college students that shows the average number of text messages they send each week. Average number of text messages that they send each week. We got men, women, we got less than 600, 670, 99, 808, 999, 1,000 or more text messages sent each week. If a person is selected at random, find these probabilities. All right, I want you to do number 51 for classwork. What's the probability that that a student randomly selected sent less than 600 texts given that it was a woman? Okay, go ahead, ladies and gentlemen. Given that it was a woman, what was the probability a student sent less than 600 text messages? Throw that into your classwork, number 51.
I think I got it.
Okay, so given that it was a woman, confines us to what row or column? Given that it was a woman, locks us into what row or column?
The third row.
Well, the woman row, correct?
Yes.
We're locked into this row. All right, so we're locked into this row. Now, given that we're locked into that row, let's answer the question. What's the probability the student selected sent less than 600 text messages a week? You would say,
What happened was I got it a little mixed up and I added the men plus the women instead of all the women.
no good, because it says given that it was a woman that was selected, locks us into the woman row. What's the probability that she sent less than 600 text messages in a week? That's going to be 61 over what? The sum of all the women. Do you agree? How many women are there in this row here? Well, you got to add them up. That gives you 79 plus 13, 92, what, 100? 100 women? And of the 100, how many sent less than 600 text messages? 61 over 100. Your answer is 61% or 61 over 100, 0.61. Anybody get that?
Wait, how did you get 100?
You got to add all the women up in this row. 61 plus 18 plus 13 plus 8. That gives you 100 women, correct? And of the 100, 61 sent less than 600 text messages a week. So the probability is 61 over 100, 0.61. Does that make sense how we got that? All right, do number 52. Given that the person selected is a man, what's the probability that the person sent more than 999 texts? More than 999 texts. So, you know what would happen, what would help a lot is if you had some total rows and columns here. Whenever you have these frequency tables, you might want to total up your rows and columns.
That would be 127 for the first one, not 117.
7. Did I add wrong? 56 plus 61?
Yes.
6 plus 1 is 7. What's 5 plus 6?
11.
11.
So how did I get 127?
You got a calculator?
Yeah, I have it sitting right in front of me.
Add 56 and 61 together. Go ahead on the machine. Tell me what you get.
It's 116. No, I added it wrong. It is 117.
Okay. I thought I was losing my mind. Thank you. The day that's 127 is the day I gotta retire. I gotta get out of the business. All right, ladies and gentlemen, number 52, the student sent more than 999 texts, given that it was a man. What column or row we locked into? Given that it was a man, that locks us into this column here, the man column. Given we're locked into the man column, then what is the
That's
probability?
a row. That's the
That's a
men
row. The row, okay, you're right, row. So you can see I'm partially losing my mind. Okay, you're right, it's a row. So then what is the probability that the man sent more than 999 texts? That'd be 16 over what?
16 over 100.
16 over 100 is the probability. Number 53. Do this one for classwork. The student was a woman, given that they sent between 600 and 799 texts. What is the probability that the student then was a woman? Do number 53.
I think I got it.
All right. Well, given that the person sent between 600 and 799 texts, that locks us where? Into what?
The second column.
Right here. We're locked into this column. Given that we're locked into this column now, what is the probability that the student selected was a woman?
18 over 36.
18 over 36 would be the probability. Mhm.
Would-
18 over 36 or 1/2, correct? Would be the probability. Are we getting this? Getting these where it says given that? Is this making any sense here?
I'm somewhat getting it.
Okay, all right. At least there's some sunlight coming through the clouds. There's
It's just
hope.
kind of confusing.
But whatever comes after the word given that, you got to remember that that's where we are confined at. Okay, we're locked into that situation. Whatever comes after the words given that. All right, so that's what you got to remember. All right, number 54. Throw it into a classwork. What's the probability that a student was selected was a man, given that they sent between 600 and 999 texts? All right, so see if you can do number 54 and I'll repeat that probability.
I think I have it.
That's,
Is that correct?
All right, well, let's take a look. It says, given that they sent between 600 and 999 texts, that's gonna lock us into let's see, given that they sent between 600 and 999 texts, do you agree that locks us into these two columns here?
yes.
We're locked into these two columns, aren't we? Because it says, given that they sent between 600 and 999 texts, locks us into these two columns. Okay, now that we're locked into these columns, what then is the probability that a student selected was a man? Well, how many men do we have in these two columns? We got 18 plus 10, which is what, 28,
28.
divided by the sum of these two columns. Do you agree? So what did you get? 28 over 59. Nice job. That's correct. All right. Hey, that's awesome. You got that. Good. All right, let's go back and look at one like number 40. Let's see, 43 is an interesting one. I wanted to look at that one.
Is this gonna be another classwork?
No, I guess I'll work this out. I'll work this one out for you, Liz Owen. At a carnival gambling booth, 2 dice are rolled and a sum of 7 wins double your money. Find the probability that the sum is 7, given that one of the numbers was a 6. Given that one of the numbers was a 6. Okay. Does anybody remember in what section the dice thing was in the dice, rolling the dice, 2 dice?
Wasn't it the last one we did?
I can't remember.
I
Was it
can't
the
really
tree
remember
diagram?
either.
It was in the tree diagram section, 10-4. Okay, so let me try to, I don't know if this is gonna work. I don't know if this is gonna work here. We'll see. Well, or what I could do is I could bring in, let's see. Find the probability the sum of 7 is sum of 7. The sum is 7, given that one of the numbers was a 6. Given that one of the numbers was a 6, what's the probability that we roll a sum of 7? Okay. All right, let's only roll 2 dice. Now, the probability they want us to compute is this one here. The probability that we roll a sum of 7, given that, this vertical line means given that one of the numbers is a 6. One number is a 6. So check this out. Given that one of the numbers rolled is a 6, do you agree that locks us into what? This row and what? This column. Do you agree? Isn't that true? Given that one of the numbers rolled is a 6, doesn't that lock us into what? This row and this column? Now, locked into these row and columns, what is the probability we roll a sum of 7? Well, that can only occur if you roll a what? A 6 and a 1? Or a what? A 1 and a 6. So, ladies and gentlemen, I got a question for you here. How many outcomes are possible between this last row and this last column? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 outcomes. Is that true? And of the 11 outcomes that yield at least 1 6 being rolled, what's the probability we roll a 7? Sum of 7. That'll be 2 over what?
2 over 11.
2 over 11. That would be your answer for that problem. But see how that conditional probability works there. All right. Listen to this question. Given that we roll doubles, when we roll 2 dice, what's the probability we roll a 3? Given that we roll doubles constitutes what? Us being locked into what? These outcomes. Do you agree? Now, what's the probability we roll a 3? Given that we roll doubles, what's the probability we roll a 3?
1 out of 6.
1 out of 6. It occurs right here. 1 out of 6. So is this, given that this conditional probability, making any more sense, ladies, on how it locks us into a situation?
It really is.
Okay, I hope it does make a little bit more sense, and because we worked several examples out, and it's only through doing a lot of problems and examples that this stuff starts to really make sense. And that's why I would encourage you to not only, do your ALEKS, but ladies and gentlemen, if you want to go in the back of your textbook at the end of each section and do some odd problems for extra practice, and then check your answers in the back of your book, I would recommend you do that. It only reinforces the stuff more in your mind. Okay. All right, that's going to wrap it up today. We looked at some multiplication rules, 2 different multiplication rules, and the one we used depended upon whether our events are independent or dependent. We also seen that experiments with replacement constitute independent events, whereas experiments without replacement constitute dependent events. And we also looked at what it means for a probability to be a conditional probability, in how computing conditional probabilities in obeying what comes after the phrase given that locks us into a situation to ultimately answer the probability question. All right, I'll open up the aforementioned quiz and exam. Make sure that you are conscious of the due dates of those things. And I'll stay on the line if there's any extra questions. If not, have a great day.
Can you also